Hi, Sun. So let us solve some problems on this chapter, so the wave mechanical model of that. So in this chapter, so what we have discussed, so we have discussed regarding wave functions and time independent Schrodinger wave equations, as well as interpretation of wave functions. And next, so we have discussed regarding what is the applications of time independent Schrodinger wave equations in case of one-dimensional blocks. And next, the last concept in this chapter is the linear harmonic oscillators and zero-point energies. Okay, so these things we have discussed in this chapters. So based on this concept, so we will solve some problems on this chapter. Okay, the formula that you have seen in these chapters are so the energy of the particles in nth state, the eigenvalues of energy in the nth state is given by E of n is equal to n square, h square divided by what is 8 ml square. Okay. And according to your linear harmonic oscillators, so there the energy of the atomic oscillators in the nth state is given by E of n is equals to n plus half into what is h nu, where n is equal to 0, 1, 2, 3, 0, 1, 2, 3, and so on. But in this case, n carries and what? 1, 2, 3, and so on. About quantum state. But here, it then starts from what? 0, 1, 2, 3, and then any numbers. Okay. So see here. First one is what? The energy of a linear harmonic oscillator in its third excited state is 0.1 electron volts. Calculate its what? Frequency. This is what? The energy of a linear harmonic oscillator in its third excited state means the energy of that particle, the energy of that linear harmonic oscillator in its third excited state is what? 0.1 electron volt. That means E of 3 is equal to how much it is? zero point 0.1 electron voltage. Okay. Then in that case, so what is the frequency of that atomic oscillator? Okay. So the formula for that is E of n is equal to n plus half into h nu. So here n carries what? 0, 1, 2, 3, and 4. But here in this case, n is equals to what? 3 is there. In third excited state, means the value of En is what? E is what? zero point 0.1 electron volt. So that was the substitute. So 0.1 equals to 3 plus 1 by 2 into h nu means the value of h is maximum 6.625 into 10 to power how much is minus 34 joule second is there. So into nu is there. So here we need to calculate the one the value of nu is. So therefore make it transportification. So nu is equal to, so we are having what is it? Nu is equals to 1 point. So that means so this is 0 point what is 0.1 electron volt is there. So if you this in order to convert in terms of joule, so you have to multiply by what is 1.6 into 10 to the power minus 19 coulomb. Okay. So 1.6 into 10 to the minus 19 into 0.1 is. Okay. So that's divided by the what is this is what 7 by 2 is there. It becomes what 7 by 2. 7 by 2 into is what 6.625 into 10 to the power minus 34. So after simplification of this term, so you will get what? The frequency of that atomic oscillator in the third excited state is given by what is 6 point, it is what? 89 into 10 to the power 12 actually. So this is about the what? How to calculate the frequency of your linear harmonic oscillators in the third excited state. Okay. Next, let's see the another example. Two electrons are confined, means existing, are situated, are located in a box of length 10 to the power minus 10 meter. Calculate the lowest energy of that system. So here, How many number of electrons are existing? Two electrons are confined in a box of length. Okay, so calculate the lowest energy of the system. Given the length of that box is how much it is? 10 to the power minus 10 meter. Okay. Next, we given h is equals to 6.625 into 10 to the power minus 34 joule second. The mass of that electron n is equals to 9.1 into 10 to the power minus 51 kg. Okay. So E of n is equal to the energy in the nth state is given by n square h square divided by what? 8 ml square. So here we are having what? Two electrons. That's why we that E of n is equals to 2 into n square h square divided by 8 ml square. So 2 into uh, n square is in the calculated energy in what? Lowest energy. Lowest energy here stands for what? N is equal to 1 h. So it becomes what? 1 square into 6.625. So into 10 to the power minus 34. Close that bracket. Whole square. So make it this square and 8 ml square. 8 is 8, m is 9.1, L square, 8 ml square. The value of your L, the length of that box is how much it is? It is 10 to the power minus 10. It should be become whole square because 10 to the minus 10 meter is there. You make it square is 10 to the power minus 10 whole square. Okay. So when you make this equation, it's 10 to minus 10 minus 10 is you make it square this one. Okay. So after making this square, so after simplifying this two terms, so you will get what? 75.3 it is what it is electron volts. 75.31 electron volts. So that is the what? The energy of those two electrons inside the silver box. So in a what? Lowest energy state, that means in the ground state. Okay. So here this 10 to the minus 10, you make it square. Okay. So after doing this simplifications, so you will get a value of what? 75.3 31 electron volts. Okay. Next, another example is consider three electrons are confined to a one dimensional box of length 1 angstrom. Calculate the lowest energy of that system. Calculate what? The lowest energy of that system. The length of that box is how much is 1 angstrom is there. So it becomes what? 1 into 10 to the minus 10 meter. This is the Planck's constant, the value of H. And mass of that electron is 9.1 into 10 to the minus 31 kg. Okay. So out of 3 electrons, first 2 electrons present in the first orbit according to your electronic configurations. So out of 3 electrons, first 2 electrons present in the what? The first orbit, that's in the ground state, n is equal to 1, and the third electrons present in the second orbit. Okay, that's the maximum of a possible number of electrons in the first orbit is what? It's what 2. That's why the 2 electrons are existing in the first orbit. The third electrons present in the second orbit. Okay. So that's why. So it's 2 into n square, z square, okay, 8 ml square, 10 to the power minus 10 whole square. So you just simplify it. So you get what? 1.205 to 10 to the power minus 17 joule. So this, if you want to convert into n what? Electron volts, just you divide by 1.6 into 10 to the minus 19 coulomb. So that's equal to what? 75.3 electron load. That's the energy of those two electrons in the volts, the first orbit. Next, the E2 is equals to what? This is second orbit. N is equals to how much it is? 2 it is. 2 square. 2 square. Number of, this is first orbit. Number of electrons is 2. In the second orbit, n is equal to 2. The number of electrons is what? 1. So it is 2 square into 6.625 into 10 to the minus 34. This is what? A whole square. So this whole divided by 8 into 9.1 into 10 to the power minus 31 into 10 to the power minus 10 whole square. So after simplification of these two terms, so you will get what? 150 electron volts in the second orbit. So the total energy of that system, the total energy of the system is 73.3 plus of what? 150. That's equals to how much it is? 223 electron volts. That's the total energy of the system. Okay? So like that, so you want to calculate what the energy in that system where when we are having what 3 electrons. Okay. Next, let us solve another problem. Reduce 0 point energy means you have to calculate the 0 point energy if the length of the box be 10 to the power minus 10 meter and there are 10 electrons in its okay. So there will be 2 electrons in the lowest energy for what n is equal to 1. When n is equals to 1 in the first orbit, so that's requires what 2 electrons. So that's why again you have to substitute all the values. Number of electrons is 2, the first orbit is n is equal to 1, and the Planck's constant is this much, and 8 ml square. So after inserting all these values, again you are getting what? 75.3 electrons. But the second orbit, out of 10 electrons, 2 electrons are what? Located to the first orbit, and the remaining 8 electrons, since the second orbit is having a capacity to have an what? 8 electrons. These 8 electrons can be present in the second orbit for n is equal to 2. Therefore, 8 into 2 square into 6.625 into 10 to the minus 34 whole square. So divided what? 8 into 9.1 into 10 to the minus 19 coulomb into 10 to the minus 10 for whole square. So that's equals to how much it is? 12.05 electron. So therefore, the total energy of the system is equal to E is equal to given plus if you just combine those two terms. So you will get 75.3 plus of what? 12.05. That is equal to 1280 electron volts. That's the energy of that electron. That system is. Okay. Next, another one more example. So when you are having what? 10 electrons. In such case, so you have to solve that problem analysis. Okay. Next is an electron is constrained in a one-dimensional box of size 1 nanometer. Obtain the first three eigenvalues in electron volts. Given the length of that box is 1 nanometer, the Planck's constant is F equals to 6.625 into 10 to the power minus 34 joule second, and the M is equals to 9.1 into 10 to the minus 1 case. So we know that eigenvalues of energy in the nth state is given by E of n is equals to n square h square divided by 8 ml square. So for n is equals to 1, so here is asked to calculate what? You have to calculate what? The first three eigenvalues in electron voltage. Okay. Next, for n is equals to 1, this is n square, n is equals to 1, and h square, 8 ml square. And this you have to obtain in terms of what is how much in terms of what electron volt. So for that you have to multiply it by what the amount 1.6 into 10 to the minus 19 coulomb. Okay. So 8 into 9.1 to 10 to the minus 31 nanometer is the 10 to the minus 9 whole square into you have to multiply what 1.6 to 10 to the minus 19 coulomb. So we will get what 0.377 electron. This is the energy of that particle. So in the first state, in the ground state. Okay. So therefore, in the second state, it becomes what? Simply write what? 2 square. N is equals to 2 make it square into multiplied by what this what I square. And the first state 0.377. So that's equal to what? 1.5 third state is what? A square into 0.77, that is equal to what? 0.393 electrons. That's the energy, eigenvalues of energy in the third state. Okay, like that. So if we have calculated what? The eigenvalues of energy in the first three orbits means ground state, first excited state, second excited state, second excited state. Okay. So like this, we have to calculate what the problems if you ask like. Okay. Next, another simple examples on this chapter is the period of harmonic oscillators. In its ground state is 2.2 milliseconds. Find the 0 point energy given h is equals to 6.625 into 10 to the power minus 34 seconds. So we know that 0 point energy is given by what? E of 0. That means according to a linear harmonic oscillators, the energy of the particles in the nth state is given by what? N plus half into what is second. Here 0 point n is equals to what? 0. So your equation becomes E0 is equals to 1 by 2. 1 by 2 h into the value of the nu is nothing but what? 2 pi by what? Nu is equals to what is 2 pi by 8. That is omega is equals to 2 pi nu. Omega is equals to what? 2 pi nu. So based on that, so you would write 1 by 2 into h into 2 pi by what? 2. But 2 pi nu is equal to, it is what is nu is the frequency is 1 by reciprocal of 3. Okay. So 1 by 2. So here he is asked to calculate the period of harmonic oscillation ground state is 2.2 milliseconds. The time period. Find the 0 point energy. So he is asked to calculate the value of E0. So therefore 1 by 2 h into 2 pi nu is there. But nu is this is nu is this is the value of 2 pi h into what? Nu is equals to write what 2 pi by I think capital T. Okay, that's time period. Therefore, so this becomes what? 6.625 into 10 to the power minus 34 into how much it is? It was 2, 2 into 3.142 divided by 2.2 into 10 power minus 3. The value of is what? The time period is what is? This one is milliseconds. So that's the after simplification of this term, so you will get a value of what? 1.5 into 10 to the power minus 31 joule. Okay. Actually, so this one, okay, this is extra h nu, h nu, h nu, but frequency is equals to 1 by 2. You no need to put that value of what 2 pi. Suppose if instead of nu, so if you are having what omega, but omega is equals to 2 pi nu, but nu is equals to 1 by 2. So in such case, so you have to write that what 2 pi. But here you don't need to write that 2 pi. So directly write what 1 by 2 into x divided by 1 by 2. So you don't write that 2 into 3.14 or 2. You just so simplify these two terms. So you will get the what? The value of P0, or the value of 0 point energy at what? At an 0 point energy. Okay, and is equals to 0. Okay, so these are the what problems. So you want to work it out. They are very simple, and thank you.